now we can talk about work. Um, so work is an important topic to discuss, because we have all the time we are actually doing work, and it's really a good idea to understand work of a mechanical system. So let's say, to start with, let's say we have let's say an ice slab, and on top of that you have another ice slab. There's a reason I'm choosing it, because let's say there's no friction between the two surfaces. Ice on top of ice, well, there will be friction, but let's assume because of this setup we do not have any friction between this. Or you don't really have to choose ice slab. You can say a block of mass sitting on a horizontal surface and does not have friction. So that is we have created an ideal situation. So with this case, let's say you apply a force F. When you apply a force F, what happens? We know from Newton's law that if we apply a force F, then in the x direction we see that it gets an acceleration F over m, given m is the mass of the ice. Now because of this acceleration, we see the velocity of the mass increases. So because the velocity is increasing, that means this guy actually gains some energy. It means it is not moving. So any moving thing has some energy in it. Anything lying at rest does not have energy. But we know that a moving car has energy. If it hits someone, it will produce heat and sound, and that heat and sound will be produced because of the virtue of the motion of the car. So if we apply a force F, then it gets some acceleration, and because of this acceleration it develops a velocity, and this velocity is nothing but a form of energy. So if we increase the force F, what do you say? If we increase F, what happens? That it has a higher acceleration, so it has a higher velocity after some time. So increasing F increases work done on the mass. By work done, we mean how much work we put on the mass so that it has some velocity, which is nothing but a form of energy. And we'll talk about that more specifically when we'll talk about kinetic energy. So the work done depends on the force applied. Also, how long you applied force. Did you apply the force when you moved it for 1 meter or 2 meters, 3 meters? The longer you apply force for longer distance, the more work you are doing on it. So you see there are two factors: how big the force is and how long in terms of length you apply, and these two factors combine together to tell you that how much work you are going to do on the mass. And friction is not really playing a role right now. Just say it's frictionless. So the work done, actually people have found out, is given as F times D, where F is nothing but the force applied, and D is nothing but distance for which force was applied. So you start, let's say, from here, and you apply your force here, and you just kept it applying until you reach distance D, and then you do this amount of work, right? But let's say, let's change few things to generalize this problem, because this is a very specific problem. Let's say you do not apply a force like that. Instead, you apply a force such that the force makes an angle theta with the x-axis. Let's call this x-axis. Okay, well, no problem. Even if you applied an angle theta, this force F is still going to provide some acceleration, and because of that it will have some velocity. The object will gain some velocity, but acceleration now is not going to be F over m, but F cos theta over m, because we are going to break up this theta, this force. This part is going to be F cos theta, and this part is going to be F sin theta, right? So now in this case, work done will be F d cos theta, right? So it's the F cos theta component that is going to do the work, and not the F sin theta component. Also, how long you applied the force. And this is actually a very general equation. So if you have something and you move it by distance d, and you applied a force F at an angle theta, this is how much work you are going to do on the object. Okay, so this is the only thing you will ever going to use when you are going to calculate the work done.